Today I'm going to talk about Treewidth and tree decompositions again, and I'm actually going to give you another equivalent definition. And this is the setting of boundary graphs. So let's say that I have a fixed set of vertices. So let's say that I know that the vertices that I can possibly use in my graphs are just 1, 2, n. Now I want to define a boundary graph. What is a boundary graph? It's just a graph on some number of vertices, so some subset of 1 to n. And I also have at most k of these vertices marked as the boundary. So I have a graph that looks like this, let's say. And I just have some part of it, this part, this is the boundary. And we have a bunch of vertices here, so maybe I have vertex 1 here, vertex 5 here, vertex 6 here. And there is no need to use all the vertices. I can have any number of vertices here, the numbers here don't have to be consecutive. The only condition that I want to satisfy is that the size of my boundary is at most some number k. So the number of vertices in the boundary are at most k. Let me just call the boundary B, so that we can talk about it more easily. I always want the size of B to be at most k. Now I want to define some operations on these boundary graphs so that I can get newer boundary graphs. Okay. So here are the operations that I want to define. Well, the first operation is a very simple one. I say that the empty graph is a boundary graph. Okay. So I have the empty graph. And of course the boundary is also empty. The second operation I have is that I can introduce a new vertex into the boundary. Okay. So introduce some vertex V into the boundary. And of course this vertex should not be in my graph from before, and I'm just adding it. And again, of course, when I'm introducing this vertex V, I have to make sure that the size of my boundary does not get larger than k. So I can introduce only if I have at most k minus 1 vertices. So let's say this was my graph before. Let's say I had some edges as well. Maybe I had vertex number 10 here. I have vertex 6 here. Maybe it was connected to this one. And let's say, just for this example, that I want to set my k to be at most 3. Okay. So I can introduce a new vertex here in the boundary. So let's say I want to add vertex number 2. I can add it here. But when I introduce a new vertex, of course I introduce a lot of edges with that vertex as well. But the edges that go out of this new vertex should always be in the boundary itself. So I cannot put 2 here and say it has an edge to 5, because 5 is no longer in my boundary. So, but I can introduce the vertex 2 here and say that it has an edge to vertex 6. And then later on, maybe I can introduce another vertex, maybe I can introduce vertex 11, and then I can connect it to either 2 or 6 or both of them, but nothing outside of my boundary. This is the introduce operation. But of course, if I just had these 2 operations, I could only add k vertices to my graph, right? Because every time I'm adding a vertex, I'm just adding it to the boundary, and the boundary cannot have more than k vertices. So this is not very interesting on its own. So we have a third operation, which is called forget. And the way forget works is that you take a vertex in your boundary and you keep it, but you move it outside of the boundary. Okay? So for example, I can say I want to forget vertex 2 here. And the way I forget vertex 2 is that I just change my boundary so that the boundary does not include vertex 2. Okay? So when I forget a vertex, the vertex remains in my graph. It's just that I'm forgetting it from the boundary. Okay, so what can I do with these operations? I can basically start with an empty graph, and I can create my new graph one vertex at a time. I can introduce vertices one at a time. But at every point, I should have a boundary that has at most k vertices in it. And whenever I'm adding a new vertex, I can only connect it to the other vertices in the boundary. So here, when I'm forgetting vertex 2, basically what that means is that whenever I'm adding any other vertices, I will never connect them to vertex 2 anymore, because vertex 2 is no longer in my boundary. Okay? Now, I can also have another operation, and I read this one with a different color because you will see that it really makes a lot of difference. And this is the operation of merging two boundary graphs. So let's say I have two boundary graphs. This is my first boundary graph, and this is its boundary. And let's say this is my second boundary graph, and this is its boundary. I can just glue the two graphs using their boundary, but this can only be done if the boundary is actually the same on both sides. So if I have the same boundary here and here, let's say I have three vertices, and let's say it's 1, 11, and 6, and here I have also 6, 1, and 11. I can just take these two graphs, and I can merge vertex 1 on both sides, merge vertex 6 on both sides, and merge vertex 11 on both sides. Okay, and then this would give me like a larger graph that contains only one copy of all these vertices that were in the boundary, and it also contains whatever was here and whatever was here. But additionally, I want to also have the extra constraint that the only vertices that are on both sides are the vertices in the boundary. Okay? So this is because I want to make sure that I don't have more than one copy of any vertex. So if I have, for example, vertex 100 here, I cannot also have a vertex 100 here. But the merge operation is basically taking these two boundary graphs and gluing them together on their boundary, which is also their intersection. Okay. Now, what can I say about graphs that I can obtain using these operations? Forget the merge operation for a second, and let's say that I have only these three operations. Right? So what am I doing? I'm starting with an empty graph, and then I'm adding something in the boundary, right? And maybe some more. And then at some point, I'm just forgetting some of the vertices that were in the boundary, and I'm just continuing like this, if I don't have this force operation. So I want to claim that I can create a graph like this with a boundary of size k, if and only if the graph has path width k. Okay, so I want to say that, and again, I'm not using the force operation, I'm only using the first three operations. So I want to say that the first three operations basically give me graphs of bounded path widths. Now, why is that? Well, I can just keep track of what happens to my boundary, right? So, let's say this is my graph. Initially, my graph is empty, so my boundary is also empty. So I just add a bag to my path decomposition, and this is an empty bag. Okay? Now, whenever I introduce something in the boundary, let's say I introduce vertex 1 in the boundary, the boundary changes. So I just add a bag with the new boundary, and I just connect it to the previous one. Now let's say I introduce some other vertex, let's say I introduce vertex 2. And let's say that vertex 2 is connected to vertex 1. Again, I just add a new bag that has the new boundary. Okay, now let's say I introduce vertex 3 and it's connected to both 1 and 2. Again, I just do the same thing. Add a new bag with a new boundary. Now let's say I forget vertex 2, so I'm changing the boundary to this. Right? I just add another bag to my path, and I just add a new boundary. And so on. Now, why does this work? Why is this a valid path decomposition of my entire graph? Well, at the beginning, of course, I have a valid path decomposition because I have the empty graph, and this is just an empty bag. Now, what happens when I introduce a vertex? Well, whenever I'm introducing a vertex, for example, here, when I introduce vertex 3, it can only be connected to the other vertices that were already in my boundary. Right? But the vertices in my boundary were here in the last bag that I had. So whenever I'm adding a new vertex, for example, I'm adding vertex 3, it can only be connected to 1 and 2. But I'm now adding a bag that contains 1, 2, and 3. Right? So this shows that every vertex in my graph is covered by my decomposition, and also every edge in my graph is covered by my decomposition. Right? Because when I'm adding vertex 3, 1 and 2 were in the boundary, and 3 had edges to 1 and 2, but then I added 1, 2, 3, which covers all of those edges. Now the last point I have to prove is that I have to prove every vertex appears in a connected subtree, but this is a path, so I just want to prove that every vertex appears in some segment of the path. Right? But that's also easy, so these bags here are basically just keeping track of my boundary. So when a vertex is introduced, it's added to the bag, and it remains there until it's forgotten. But as soon as it's forgotten, it will never be introduced again. So every vertex appears in a connected segment. So this basically proves that if I have a boundary graph with these first 3 operations, and my boundary size never exceeds k, then the graph has path width k. Path width, actually k minus 1, if you want to be very specific about that, because in the definition of width we said that we have minus 1. Okay, but what about the opposite side? So let's say I have a path decomposition, and let's say that this path decomposition has bags of size at most k. Can I create that graph using these operations of boundary graphs? And again, the answer is yes. The only difference is that when you get your path decomposition, you have to first make it nice. And you remember the definition of nice from last session. The definition was that every one of these bags should be different from any of its neighbors, so its parent and its child, by at most one vertex. And we saw that we can take any nice tree decomposition and make it nice in linear time. We can do the same thing with path decompositions. So I just take my path decomposition, I make it nice, and then again I look at it as the sequence of events on my boundary. So what has happened on my boundary? And that tells me how to create the graph as a boundary graph. So it's an if and only if type of situation. Okay, now of course you can imagine what I want to do with this last operation, with the merge operation. I want to say that if we have the first 3 operations, then we get path widths. But if we have all 4 operations, then we get Treewidth. Okay? So, what does merge do? Merge just takes 2 different graphs, and these graphs have the exact same boundary, and just merges them on the boundary. Okay? So let's see what happens if I do the same thing that I was doing here, but let me create my path from bottom up. Okay? So again, I'm going to do the same example. let's say I have a boundary graph here, and I have a boundary graph here, and at some point I want to merge them, okay? But for now, let's just say that I'm doing some operations here. So let's say I add vertex 1 into my boundary, and I want to put my path decomposition from bottom up. So I start with the empty boundary in my path decomposition, and I added vertex 1 in the boundary. So I just added as a bag here, but this is now a parent of the previous bag. So I'm looking at it in this direction. Okay, let's say now I add vertex 2 and I connect it to vertex 1. Okay, so here I will just get a bag that is 2 and 1. And let's say I add vertex 3 and I connect it to both 1 and 2. So here I will have a bag that has 1, 2, 3. Now let's say I forget vertex 1. So 1 is out of my boundary now. So I just get 2, 3. Okay? On this side, let's say I do something similar. So I start with an empty bag. Let's say I first add vertex 4. So I will have 4 here. Let's say then I add vertex 2 and I connect it to 4. So I will have 2, 4. Then let's say I add vertex 3 and I connect it to 2. So I will have 2, 3, 4. Okay? And finally, just to make the boundaries the same, I'm going to say I forget vertex 3. So my boundary becomes, I forget vertex 4. So now my boundary becomes something like this, and I have 2, 3. Okay, so these are the past decompositions that I had. And now these are two boundary graphs whose boundary is the same. And also, they don't have any intersection outside of the boundary. So outside of the boundary, here I only have vertex 1, here I only have vertex 4. So they satisfy all the requirements for merge. I can merge these two graphs, and as I said before, merging will just merge vertex 3 of both sides and vertex 2 of both sides, and keep the one copy of the other vertices. So when I merge all of this, I will get vertex 3 and vertex 2 that were connected to each other on both sides. And then I have vertex 1 on this side that is connected to both 3 and 2. And I have vertex 4 on this side, which is only connected to 2. So this is the graph I will get after merging these two boundary graphs. And what is its boundary? Its boundary is just 2 and 3. So this is my boundary. Okay? But let's look at our past decompositions. I had a past decomposition for each one of these two graphs. And now I've merged them. How can I merge the past decompositions? Well, I can just take this same bag that is the root of both of my past decompositions, and I can create a copy of it, and then let that one be the parent of both of these. Right? But as you see, I no longer have a past decomposition. Now, because of the merge operation, I got a tree decomposition. Now, how can we prove that this is actually a tree decomposition? It's a valid tree decomposition. Well, each part was a valid tree decomposition before, and the only vertices that were shared between the two graphs were the vertices that are in the boundary. And I put all of those vertices here at this bag at the root. Right? So it's now easy to just verify that all the conditions of a tree decomposition are satisfied. So for example, for the condition that every vertex should appear in a connected subtree, every vertex either only appears on the left, which is in a connected subtree according to just induction, or only on the right. which we can also solve inductively, or it's in the boundary, so it appears in a connected subtree here that is connected to the root, and another connected subtree here that is also connected to the root. So overall, it's connected. Okay. And now again, we can think about this from the other way around as well. So if I have these 4 operations and I create a boundary graph with boundary size at most k using these 4 operations, I showed that the Treewidth is at most k minus 1. But let's do the opposite. Let's say I give you a tree decomposition such that every vertex has at most k vertices. Every bag has at most k vertices in it. So I can again first make the tree decomposition nice. And remember that when we were making the tree decomposition nice, we were also saying that every node has at most 2 children, right? But now I can define my nice tree decomposition in an equivalent way that also uses these words. So I can say a nice tree decomposition is just a tree decomposition such that, well, the first condition I want is that I want every leaf to be the empty set. So every leaf bag is empty. That's my first condition. But now, what other types of bags can I have? I can say I can have an introduced bag. So I just use the word introduce as a label for my bag as well. So I want to say every non-leaf bag is one of these cases. So the first case is that it's just an introduced bag. Now, what does an introduced bag do? So for example here, remember I created this bag when I introduced the vertex 1. Right? So this bag, I just added something to the boundary. So it has exactly 1 child, and it has 1 more vertex than its child. So an introduced bag is just like a bag B. And let's say that B has only 1 child C, right? And the vertex set of B is just the vertex set of C union with some new vertex B. Okay, and this B was not in C itself. I'm not going to write that, but just remember it. Okay? So I can also have a forget bag. So what happens when I forget something? For example, here, my boundary was 1, 2, 3, and then I forgot vertex 1. So my boundary just became 2 and 3. So again, it's just a bag that has a single child, but now it has 1 vertex fewer than its child. So forget is the same thing. It's a bag B that has a single child C, but now C has a vertex that B doesn't. Sometimes people use this to show that it wasn't in the original set. Maybe I can do this with disjoint union. Okay. What other kind of node I can have? Well, I can of course have a merge node. But what does my merge node look like here? It's just a bag that has exactly 2 children, and both of its children have the same set of vertices as itself. So the last type is merge. And it's just a bag B that has 2 children. Let's call it C1 and C2. And the vertices in C1 are the same as the vertices in C2 and the same as the vertices in B. Okay. Now, this is a little bit different from the definition of nice tree decomposition that we saw last time, but the differences are very minor. Right? So, again, the same algorithm that I talked about last time can be applied here. If you're given a tree decomposition, you can make it nice with this definition, and you can make it nice in linear time. So after you make your tree decomposition nice, then it's basically telling you the steps for creating your boundary graph. and everything is just like the case for passwords. So, yeah, the theorem here is that if you create a boundary graph of boundary size at most k using only these first three operations, then you get a graph of path widths at most k, and vice versa. And if you use all four operations, you get a graph of Treewidth at most k minus 1, sorry, most k minus 1. Okay. So now let's see if we can use these ideas, and especially this new definition of a nice tree decomposition, to come up with better dynamic programming algorithms. So last session we saw a dynamic programming algorithm that was solving the maximum independence set problem, and we saw that it got ugly and the overall runtime was something like 4 to the power of k times n. And now I want to see if I can make it any better with this definition of nice. So this is our problem, maximum independence set, and we want it to be parameterized by Treewidth. So I've given you a graph, and I'm guaranteeing that this graph has small Treewidths at most k. And as I said before, you can always compute the Treewidths in linear time FPT, so I can also assume that I have an optimal tree decomposition here. And the tree decomposition also, let's say, has n banks. And now I ask you, what is the size of the largest independent set in this graph? Okay. Now, we're going to do basically the same dynamic programming that we did last time, except that we now have a little bit more help in our nice tree decomposition. And we know what this means. Okay. Oh, and by the way, another thing. Last session, I defined this concept of the subtree of every bag and the subgraph corresponding to that subtree. And you can now also see that that's basically the boundary graph that was created until the point where that bag became our boundary. Okay? So you can just have these two intuitive ways of looking at the graph at the same time. Okay. So I have my tree decomposition and my graph, and I want to again define my DP. So I say that for every bag B in my tree decomposition, and for every mask, which is a subset of the vertices of B, I just define DP of B and M, and I want to define it exactly as before. I want to say that this DP is what? It's the size of the largest independent set, let's call it I, of which graph? Of the subgraph that corresponds to this bag. Okay? Such that the intersection of that independent set with my bag is exactly my mask. Okay? So basically the idea, again, just like last session, is that for the vertices that are in my bag, or equivalently for the vertices that are in my boundary, I know exactly which ones I'm going to put in my independent set, but for everything else, I have a choice, and I have to try to find the best possible independent set. Okay. Now let's see how we can compute this dynamic program. Well, first of all, let's see what happens at a leaf. Of course, I take my tree decomposition and I first make it nice so that I can say that my leaves are empty. So if my leaf is empty, then all the DP values at the leaves are just 0, right? Because I can't take anything. So that's a very simple case. Now, let's look at the other types of nodes. Let's look at an introduce node. So if I have an introduce node, I have this bag B, and it has only one child. This child is C. And V has one vertex that C doesn't. So there is one vertex here, let's call it V, that is not here, and then a bunch of other vertices, and these vertices are also in C. Okay? But now I want you to again think about this in terms of the boundary graph. Right? So when I added this V to my tree decomposition, I basically have a boundary graph that corresponds to everything that happens below V. Right? And then there is, of course, the rest of my graph. So there are some things above V as well. Right? I can maybe have a merge node, I don't know, some other nodes above this. But you can think of all of this as something that is going to happen in the future. So just think about the operations that we were doing on the boundary graphs. I've done some operations and I've got the graph until this point, and this is the boundary of the graph until this point. And everything above here are the things that I'm going to do in the future. So I just don't think about that, and I say until this point in time, so in this boundary graph. And assuming that I know exactly which set of vertices from the boundary I'm going to put into my independent set, now what is the maximum size of the independent set? Okay. But now let's look at it. So when I created this, of course, I had another boundary graph which corresponded to this part and had C as its boundary. And then I just introduced the vertex V, and I got this new boundary graph. So what has changed in my boundary graph? It's just that I have this one more vertex and some edges from this vertex to other vertices in this boundary. So that's all that can possibly change. Okay, now what can I say? So I want dp of bm. So in this boundary graph, I want to take the set M from the vertices in V. Of course, there are two cases. Either I'm taking this extra vertex V, or I'm not taking it. Okay? So what happens if I'm not taking it? I just have one new vertex, and I'm not taking it in my independent set. So I can just look at the answer from before. Right? It doesn't matter if I have this vertex or not. I'm not putting it in my independent set. So this would just be dp of Cn. Right? Just look into the previous boundary graph. Now, what is V is in M? What if V is in M? Well, V has a bunch of edges. Right? So first of all, I have to make sure that these edges don't make a problem for me. Right? So if I have V in my independent set, and I also have some other vertex here that is in my independent set, and they're connected, then it's no longer an independent set. And in that case, I should just say my answer is minus infinity. Okay? So my answer is going to be minus infinity if V is in M, and there is also some U that has an edge to V, and U is also in U. Okay? Now, what if I don't have that case? So what is my other bias here? So I know that V is going to be in my independent set, and I know that none of the neighbors of V are in my independent set. So again, I can just take an independent set from the previous graph, and none of the neighbors of V are in it. So I can just add V to that independent set and do +1. So this would just be dp of C and M minus V, of course, because V didn't exist here, so I have to remove it from my mask, and +1. Okay? So this is how I would handle an introduce node. So we now know how to handle leaf nodes, We know how to handle introduce nodes. And actually, the thing that I really want you to see here is how much time we're spending. So for every DP variable, this is going to take constant time. This is just going to take all k squared time, right? Because I have k vertices here, and I have to just check k squared pairs at most. And this part is again constant time. So for every one of my DP variables until this point, I'm spending at most k squared time. But of course, I have to go back and talk about what happens at the forget node and what happens at the merge node. So let's do the forget node now. Okay. The forget node has a very similar situation, except that now the child has one vertex node. Okay? But what do I know about the boundary graphs that were rooted at any of these places? So you see, this was a forget node. So the only operation that I did on the boundary graph was that I took V and I kicked it out of my boundary, but it's still in my graph. So the graph corresponding to this node and the graph corresponding to this node are the same. Right? So now I want to find dp of B and M. So what does this mean? This means that I know which subset of my vertices from the bag B are going to be in my independent set. So that also tells me which subset of vertices in C are going to be there, except that I don't know about this new vertex B. Right? For every other vertex, I already have the information whether it should be in my vertex, whether it should be in my independent set or not. But now, I just don't know about this. And the graphs are the same. So I can just try both cases. So just try dp of C and M, and also try dp of C and M union with this vertex B. And just take the maximum of both of these cases. Right? Because either I put B in my independent set or I don't. And the graph hasn't changed. So that's it. Again, constant time. Okay. Now we get to the merge case. So I need to draw a completely different picture. So in the merge case, I have some bag B, and this bag has two children. Let's call this one C1, and let's call this one C2. And of course, again, there is some future going on afterwards. But here's the thing. The two sides had basically two different boundary graphs. So let's say this was the boundary graph of this side that had C1 as its boundary. And let's say this was the boundary graph of this side, which had C2 as its boundary. And also, we know that the set of vertices in C1, C2, and B are the same. So whatever I had here, let's say I had these three vertices, I have the exact same three vertices here and here. Okay? And then at this merge node, I'm just merging these two graphs by putting these vertices, by merging corresponding vertices of the boundary of both sides. So this is what I want to compute my dp for. So let's say I want to compute, again, dp of B and M. What does this mean? Well, it means I know which vertices in B are supposed to be in my independent set, right? In the merged graph. But then, if I know which vertices of B are supposed to be there, I know the same information about C1 and C2 because they have the exact same set of vertices. So from this graph, from the boundary graph on the left, I have to just take dp of C1 and M, right? I just take the largest possible independent set that I can from this side while respecting the mask that I had. And I do the same thing on this side. So plus dp of C2 and okay, why can I do this? Because the only intersection between the two sides were in these boundaries, right? Or another way of looking at it, if you just want to look at it as a tree decomposition, is that the only vertices that appear both on the left and on the right are the vertices that are appearing in the bag B itself, because every vertex has to appear in a connected subtree. Okay? So I can just take the best possible independent set here and the best possible independent set here, and I can do this independently. But there's one last point. So the vertices in M itself were counted twice. They were counted here, and they were also counted here. But when we did the merge, we have to count them only once. So this gets minus the size of them. Okay? Again, constant time for computing each one of the dps. So now, what is my total runtime? I saw that in the worst case, which was in the introduced case, I spent k squared time to compute one of my dp variables. So my total runtime is just O k squared times the number of dp variables. But how many dp variables do I have? Well, I have n bags, and how many masks can I have? I can have 2 to the power of k masks. So it's just k squared is really negligible, so it's basically 2 to the power of k times, which is much better than just using a normal tree decomposition and getting a formula. Okay. But I did all of this because I wanted you to really have a good intuition about how nice tree decompositions work and how they're related to that concept of boundary graphs. So whenever you're designing dynamic programming, you can just keep all of these concepts in mind. So let's just do another example really fast. Let's say I want to do tree colorability. Parameter the same, my parameter is the Treewidth, but I want to do tree colorability. What does this mean? It basically means I give you a graph, it has bounded Treewidth, you have the tree decomposition, whatever, and I'm asking you, can you color the vertices of this graph with 3 colors so that no 2 vertices that have an edge between them have the same color? Okay? So that's the question, and of course it would be nice if we find the coloring itself as well.
Sorry, can you ask why was the number of masks was to the power of k?
Oh, because every bag has at most k vertices in it, and every mask was just a subset of the vertices of a bag. So at every bag I can have at most 2 to the power k masks. Okay, so let's say I want to solve tree colorability. And let's say my answer is just a Boolean, whether the graph is tree colorable or not. Okay? But of course I can find the coloring itself the same way, but let's just focus on the Boolean. Now I'm going to define a very simple dynamic programming, and it's again the same idea as before. So I'm going to say, consider any bag. So let's say I have a bag B, and the set of vertices are just V of B. Okay? I just consider all the colorings of the vertices in my current bag. So this would just be a function from V of B to 1, 2, 3, just giving a color to every vertex. Right? And let's say I call this function F. Now I want to say that for every bag, and also for every function f that colors that bag, I want to define some dp variable. and dp of b and f is basically Boolean, and it tells me whether I can color the graph that is corresponding to this bag so that the vertices in this bag are colored according to f. Okay? Is it possible to color the graph that we have that corresponds to this bag? You can think of it as the graph that corresponds to the subtree, or you can think of it as the boundary graph that we had when we added this bag. Is it possible to color that graph such that the vertices in this bag are colored according to f? Now, this is another case that you can probably solve without a nice tree decomposition, but your algorithm would look awful and it will have like an awful dependence on k. So let's say I made my tree decomposition nice with this definition, and I'm going to use this nice tree decomposition. Now again, I have to talk about what happens at leaves, at introduced nodes, at forget nodes, and at merge nodes. So if I have a leaf, my leaf is empty. So the only coloring of the empty leaf is just like the empty coloring, right? And the answer for that is yes, because like not coloring is a valid coloring for an empty graph. Okay, so at my leaves, all of my dp variables are just yes, 1. Okay, what happens if I have an introduced bag? So I have a bag B, and it has a single child C, and B has one node, one vertex more than C. Okay? And I want to find dp of B and F. Now, F is telling me how to color every one of these vertices, right? But all of the vertices in C are also in B. So F is also telling me how to color the vertices in C. Right? So this dp is just going to be the dp of C and F. But when I take F for C, I have to remove this one vertex from my function. So F restricted to vertices of C. Okay. But this is not always the case, because again, we have to do some checks here. And the check is, suppose this new vertex is connected to some other vertex, and F is giving both of them the same color. Right? If that happens, then my answer should be no. Okay? So if V is connected as an edge to U, and F of V is equal to F of U, then my answer is no. 0 or false. And otherwise, my answer is this. Oh, I'm sorry for writing it in the wrong order. This, otherwise this. Okay. So, how much time does this take to compute this dp? Again, I have to go over every pair of vertices and see if they have an edge and the same color. So this is going to take k² time for computing one dp. Okay, now let's do the other cases really fast. So let's say I have a forget node. So now I have my vertex B in bag C, but not in bag B. Again, the situation is very similar, because when you have a forget node, the graph corresponding to C and the graph corresponding to B are the same. It's just that your mask only gives you, or your function f only gives you the coloring of vertices in B. So you just have to figure out how to color this last vertex. But you only have 3 choices. You either color it 1, 2, or 3. Right? So dp of B and some f is just going to be the OR for I from 1 to 3 of dp of c and f union with vi, by which I mean I keep the function f except that I say now vertex v has color I. Okay, so I just have to try and see what color I can give here. And of course I have to take the OR of all of the cases, because even if one of the colorings works, I have a coloring of the whole thing. Okay, finally merge. Merge is much easier now. So I have B, and I have two children, C1 and C2, and they have the exact same set of vertices as in B. Okay? So now if I want to compute dp of B and some f, f is telling me how to color these vertices. But these are the same as the vertices here and the vertices here. So I know the color of all these vertices. Right? And then I have to consider the boundary graph that corresponded to this side and the boundary graph that corresponded to this side, but they don't have any vertices in common except for the vertices that are already colored by f. So I just have to figure out if I can color both sides correctly. So dp of bf is just dp of c1f and dp of c2. Right? Okay. Runtime analysis, exactly the same as before. I'm spending at most k-squared time for each one of my dp's. The only difference is that the number of dp variables is now different. So I have O of, okay, so how many bags can I have? I can have n bags. How many functions f can I have? So every function f just maps the vertices in a bag to 3 colors. But I have at most k vertices, so I can have at most 3 to the power of k such functions. So it's just n times 3 to the power of k times k squared. And of course it's FBT and it's also linear and everything. So you can use the same ideas to solve a lot of other problems. You can solve minimum vertex cover like this, you can do click, you can do dominating set. All of these things work exactly like this. Okay, but now I want to show you kind of a different strategy, which uses 3 decompositions, but it uses 3 decompositions in a different way. Consider a problem from Markov chains, and this is called heating probabilities. So I have heating probabilities, and my parameter is Treewidth as usual. And by the way, all the algorithms that I showed you for Treewidth, of course, also work for pathwidth, because path decomposition is a special case of tree decomposition. It's just that you don't have the merge. Okay, so what is the heating probabilities problem? So let's say that I give you a Markov chain, and a Markov chain is basically a directed graph where you have probabilities on every one of the edges. Okay? And also the sum of the probabilities of edges going outside of every vertex is 1. So I have this vertex, let's say vertex 1, 2, 3. And let's say with probability 1/4, I go from 1 to 2. With probability 3/4, I go to 3. From 3, with probability half, I go to 2. With probability half, I go to 1. And let's see, from 2, let's say with probability 1, I go to 4. And from 4 with probability half, I go back to 3 with probability half, I go to 5. And when I get to 5, I always stay there with probability. Okay? So this is a Markov chain. A Markov chain is just a directed graph such that you have probabilities on all of the edges, and the sum of outgoing probabilities from every vertex is 1. Now, of course, you can imagine what we want to do with this. We want to start at some vertex and then just follow the edges according to their probability. So if my starting vertex is vertex 3, I just say, okay, with probability half I go to 1, with probability half I go to 2. So I just flip a coin. If it's heads, I go to 2. Now when I'm at 2, I can only go to 4. So I go to 4. And then again I flip a coin and I either go to 5 or go back to 3. Okay? So this gives me a random walk. I have a walk on this whole graph. I'm going all over. And of course this walk is random because every time I have to randomly choose which edge I'm going to take out of the current vertex. So now let's say that I have some target vertex. So let's say my target vertex is 5. And I want to compute the probability of ever reaching this target vertex. And I'm going to call that P of ut. So T is my target vertex, and P of ut is the probability that the random walk reaches T. And this is assuming that the random walk starts at U. So if I have a random walk that starts at vertex U, what is the probability that I eventually reach my target? That's the problem I want to solve. Okay, so what are my inputs? My inputs are a Markov chain and also one target vertex. And what should be the output? Well, for every vertex U, I want you to print this probability. What is the probability that I get to my target if I start at the current vertex?
After using number of steps, so we're not bounding number of steps.
No, we're not bounding the number of steps.
Eventually we come to this.
Yeah. So there is no bound on how many steps you can take. I don't want to do matrix multiplication or anything like that. It's just what is the probability that the walk that I start from vertex U eventually gets to T, and I don't have a bound. I don't say like after 100 steps. It can get to T at any point. Yes.
In that case, this graph itself would then the probability to eventually arrive at any other vertex except the one is 0.
No, well, here's the thing.
If it's not well connected, then it's...
Yeah, but my target is 5, right? So if I start at 5, the probability that I see 5 is definitely 1, because I see it already on my side. If I start at 4, there is a half probability that I see 5 in just one step, but actually the probability of reaching the target is more than half, because for example, I can take this path also and then go to 5. So I'm just taking the sum of the probabilities of all the paths that start from this vertex and end at the target. And I'm asking what is that probability? Okay. So, of course, I want to parameterize this by the Treewidth, but before that, let's see if we can solve this without any parameterization and what kinds of solutions we can get if I just want to solve it in the general case.
If graph is strongly connected, that is 1, right?
If the graph is strongly connected, yes, it's 1. But I'm not assuming that the graph is strongly connected. So let's see if I can write some, let's say, equations for this. So first of all, I know that P of TT is 1. Right? That's very obvious. If I'm already at the target, I have, of course, reached the target. But now let's say I have some vertex u, and let's say that it has edges to a bunch of other vertices, v1, v2, to vr. And let's say that the probabilities of these edges are p1, p2 to pr. Okay. What can I say about the probability of going from u to the target? And let's just assume that u is not the target. Right? Because if u is the target, I already have it. Okay. So just look at what happens in the first step of the path. I start at u with probability p1, I go to v1. And then from there, the probability of reaching the target is just p of v1t. Right? With probability p2, I go to v2. And then from there, I have another probability and so on. So the equation that I can write is that the probability of reaching t from u is just the sum over I from 1 to r of this pi times the probability of going from vi to t. Right? But now I can't just solve this using dynamic programming because I might have a cycle, right? If I didn't have a cycle in my graph, and I just had these equations, then I could sort my vertices in a topological order and just compute these values with dynamic programming. But I might have a cycle, and actually here I have this cycle, or this cycle. But okay, that's fine. I can just look at each one of these probabilities as an unknown real variable, right? And then I basically have n minus 1 equations, or n equations, if I also count this one, and I also have n unknowns. So I can, and these are all linear equations, of course, because I know that these pi's are some constants that were given to me in the input. So I just do Gaussian elimination, and I just solve the system, right? I have to be a little bit careful when I'm doing Gaussian elimination, so one pre-processing that I can do is that I can first find all the strongly connected components of this graph. And then I can say that basically if you have a vertex u and there is no path from u to t, then this probability should be 0. So I can add those zeros to my equations as well. But at the end of the day, I just have n equations, n unknowns, and they're linear equations. I just do Gaussian elimination. Okay, but how much time does Gaussian elimination take? So of course, you have the naive algorithm, which takes NQ, but there is a Gaussian elimination algorithm that takes n to the power of omega, where omega is the matrix multiplication constant. But again, we're not interested in any of these. It's just that my point is it takes too much time, right? So now this is an example of a problem that wasn't NP hard in the beginning. I had, let's say, a cubic algorithm, and this is a polynomial time algorithm. So the problem is solvable in polynomial time. But I just feel like n cube or n to the power of omega is too much. So maybe I want to parameterize this now. And let's say I want to parameterize it by 3 bits. So my goal is no longer just to get an FPT algorithm. I want to find an FPT algorithm that is faster than those. Okay. How can we use Treewidth? So you might be able to come up with some sort of clever dynamic programming, but I want to use a different technique, and the technique is called kernelization using Treewidth operations. So I want to do kernelization. And in kernelization, if you remember, we just wanted to get rid of vertices and make our graph smaller. So how can I remove a vertex from my Markov chain? Let me just, and again, don't think about Treewidth yet, just think about the kernelization part. I want to remove some vertex. So I have some vertex u, and this vertex is not my target vertex, and I just want to get rid of this one vertex, but I want to do it in a way that the probabilities don't change. So for every other vertex, I want the probability of reaching the target to remain the same. How can I do that? Well, I can just look at all the predecessors of u. So let's say v1, v2 to vt. These all have edges to u. And I can look at all the successors of u. So w1, w2, to let's say ws. Right? And for each one of these edges, I have some probability. Right? So I have, for example, probability p1 here, p2, pt. And here, let's say I have q1, q2 to qs. Okay. What happens if I remove the vertex u? So previously, when vertex u was here, there was a path with probability p1 times q1 that went from w1, that went from v1 to w1. Right? So if I remove vertex u, I can just add a direct edge from v1 to w1 with that probability, with probability p1 times q1. Right? And I can do the same thing for every pair of a predecessor and a successor. So in order to remove the vertex u, I can just say that I take the predecessor vi and the successor wj, and I just add a direct edge with probability pi times qj. Right? And then I can remove the vertex u, and nothing changes in the rest of the graph. So this actually gives me like kind of a kernelization algorithm that doesn't even have a parameter, right? I can take any vertex I like, and I can just remove it. Of course, except for the target vertex. Okay, but after I remove this vertex u, let's say I recursively compute the probabilities of reaching the target from every other vertex. But I still need that probability for vertex u itself as well. Right? So I have to put u back. So I first remove u, and I add these edges, and I compute all the probabilities. But now I just put u back, and I don't add the edges that were coming into u, I just add the edges that were going out of u. Right? Because for every other vertex, I already know the probability. I just want to compute the probability for u. And the probability for u was just the sum of probabilities for these vertices times the probabilities of edges to them. So I can just, after computing everything, put u back and compute the value for u as well. Okay? So, how much time does this take? How much time do I need if I want to have an algorithm like this to compute all of the probabilities of reaching the target? Well, how many vertices do I have to remove? I have to remove n minus 1 vertices. Right? So, let's just call that n. Now, how much time do I spend removing every one of these vertices? So it's basically t times s, because I have to add t times s new edges, right? But t was the number of predecessors and s was the number of successors. In the worst case, I might have n predecessors and n successors. So in the worst case, each removal takes n squared time, and I'm doing n removals, so it's n cubed. Okay? So basically, this is very similar to Gaussian elimination. We didn't get anything better than that. But we got one important point here. And the important point was, when I was removing this vertex u, the time I spent to remove the vertex u was only dependent on the degree of u. So it was the number of predecessors times the number of successors. And when I was doing my runtime analysis, I did a very naive thing, and I just said, imagine that I have n predecessors and n successors. But if I can somehow remove these vertices, remove my vertices u, in some order that ensures that whenever I'm removing the vertex, it has small degree, right? So let's say that I always know that t is at most some number d and s is also at most some number d. So whenever I'm removing a vertex, it has at most d predecessors and d successors. Just imagine this for a second. I'm not going to tell you yet how to do it. I'm just saying imagine this. Then what would be my runtime? Well, I have to remove n vertices, and each one of them is now going to take d squared time. So my runtime would be n times d squared. So if only I could find some ordering for the removal of vertices, so that whenever I'm removing a vertex, the degree of that vertex is small, then I could have a linear time algorithm instead of a cubic time. And this ordering is what I'm going to get from my tree decomposition now. Okay, so let's say that I have a tree decomposition of my Markov chain. And I don't need the tree decomposition to be nice anymore. I just take any tree decomposition. So let's say this is a tree decomposition of my Markov chain. Just to show it's not nice, I'm going to add tree chain. Okay. I want to identify a vertex that has a small degree, because I want to always remove vertices of small. So I just go to one of the leaf nodes, and I look at all the vertices that appear in this leaf node. Let's say I have vertices 1, 2, and 3 in this leaf node. And I just ask, do these vertices also appear in the parent? So if all of these vertices also appear in the parent, so let's say the parent is 1, 2, 3, and 4. If all of the vertices that appeared in this leaf also appear in its parent, then I don't need this leaf in my tree decomposition. Right? I can just simplify my tree decomposition. This leaf is not contributing anything. All the edges that were covered by this leaf and all the vertices that were covered by it were also covered by its parent. So, if this was the case, I just remove this leaf, and now I have a simpler tree decomposition. But what is the other case? The other case is that I find some vertex in this leaf, let's say vertex 5, that does not appear in its parent. I claim that this is the vertex that I want to remove. So if I take this vertex 5 here, and it appeared in this leaf, but it didn't appear in its parent, what does this tell you? It tells you that it only appears in this leaf, because it has to appear in a connected subtree. So this vertex is only appearing in this leaf. So how many neighbors can this vertex have? Well, all of its neighbors should be in the same leaf, because every edge should be covered by some band. So that means that the number of neighbors that this vertex can have is at most the Treewidth. So the degree of this vertex in degree plus of degree is at most the Treewidth. So I take this vertex and I say this vertex has small degree, I remove this one. And then I just continue the same process. Every time I just take a leaf, try to find a vertex that only appears in this leaf. If I don't find a vertex like that, I remove the leaf. If I do find a vertex like that, I remove that vertex from my Markov chain. So this ensures that I have an elimination order, an order for removing the vertices, so that every time that I'm removing a vertex, its degree is at most the Treewidth. But we saw that our runtime was O of n times d squared, where d was the bound on the degree. So now my total runtime is just O of n k squared, where k is the Treewidth. And this is a fixed parameter tractable algorithm, an FBT algorithm, you have the same ringtone as me, where it's linear time, so the dependence on n is linear, but now we're getting a k-squared factor. But again, the whole point of working with parameterized algorithms was that we were thinking k is supposed to be much smaller than n. So if I have bounded Treewidths, I can solve this problem in linear time, even though without bounded Treewidths, my algorithms took n cube or n omega. Yeah, and this whole idea of elimination order and finding like vertices of low degree and removing them using the tree decomposition, this is what's called tree decomposition based kernelization, because you're doing kernelization and you're doing it using the tree. Let's see if I have time to cover one more topic. Yeah, I can probably just say a few words about how this can be extended. So remember, I had a solution for the general case of this problem, which was just based on writing linear equations, a system of linear equations, and doing Gaussian elimination. So this problem is a special case of solving systems of linear equations. So the next step is to say, suppose that I have a system of linear equations, and my system has bounded Treewidths. So it's not necessarily a system that comes from a Markov chain. Can I solve a general system of linear equations that has bounded Treewidths using this approach? And of course, I have to define what I mean when I say a system has bounded Treewidths, because Treewidths is for the graph, right? But here's the thing. When we were removing vertices here, what were we removing from our system of equations? We were basically removing variables, right? It's like the middle school way of solving systems, where you take one variable and write it in terms of the other variables and then remove that one variable, right? So let's define that. We actually have a concept which is called a primal graph. And if I give you a system of equations, any kind of equations, the primal graph is just a graph that has one vertex for each variable. So let's say I have x plus y is 2, z plus w is 4, x minus z is 6, w plus y is 7, whatever. So I just create a graph where I put one vertex for each one of these variables. So I have x, y, z, and w. And then I put an edge between two vertices if they appear somewhere in the same equation. Actually, let me also add y here. So here I have x and y, so I just add an edge between x and y. Here I have y, z, and w, so I add an edge between any pair, between y and z, y and w, and z and w. Here I have x and z, and here I have y and w, but I already had an edge. So this is called the primal graph of this system of equations. And yeah, so if you have a system of equations whose primal graph has bounded Treewidths, then you can basically find an elimination order. You can find an order for eliminating the variables in your system, so that whenever you're taking one variable and you want to get rid of it, it only depends on the other variables where d is your Treewidth. So whenever you're eliminating a variable, you're replacing it with some expression that has length at most d. So you're eliminating the variables without making the length of your equations too long. And basically the same idea here shows that you can solve these kinds of systems in linear time as well. Okay, so that's all for today, and in the next session we will see some randomized techniques in parameterization.